So we're going to have a quick look at a video on just the various different formulas associated with organic compounds. This always causes a bit of confusion. So we'll just sort of run through the different formulas first of all, so that we're clear on what they actually are, and then we'll see how we actually draw these formulas or write them, depending on what information the examiner gives us. Right, so we'll look at the simplest of the lot first of all. That's empirical formula, and that is just very simply the simplest whole number ratio of atoms in a molecule of something. So if I had a molecule, this is a molecule called benzene, and it's C6H6, the empirical formula of that very simply would be CH. So it's just the simplest, it's a 6:6 ratio, simplest is 1:1 ratio, we don't write the ones in. Likewise, if I had something C3H6, the simplest whole number ratio there would be 1:2, so it would be CH2 is how I would represent the empirical formula of that. Now, there are also examples where the empirical formula, molecular formula would be exactly the same. So if I took something like C3H8, okay, which is propane, I can't simplify that any further in terms of whole numbers. So the molecular formula is C3H8. Well, the empirical formula is also C3H8. Sometimes students get a little bit confused and flustered in the fact that both would be the same, but that's perfectly reasonable and happens very frequently. Okay, the molecular formula then of something is the actual number of atoms in the molecule. So for example, this would be the molecular formula of benzene. There are 6 carbons and 6 hydrogens in it, and likewise the same for propane there. The molecular formula would be C3H8. There are 3 carbons, 8 hydrogens in a mole of that, or a molecule. Right, then you have your displayed or structural, which is one that students use a lot, where you draw out the atoms and you draw all of the atoms and all of the bonds. So if I take this molecule here, this is, we have 5 carbons in our longest chain here, so we have a pent, it's an alcohol group, and we have a methyl group also here on position. So the alcohol group is here, so it's a pentan 1-all, and we have a methyl group in position 1, 2, 3. So we have 3-methyl pentan 1-all, and you should be able to, from your naming and drawing, to switch between those two types of formula. So, or the name and the displayed structure. I haven't drawn in the hydrogens here. Okay, just save me a little bit of time. But obviously you would, in an exam, have to draw in all the hydrogens. And if it does ask you to draw all the bonds, frequently, if there is one bond that students forget to draw in the exam, it is a bond between an O and an H, because we're so used to just simply writing OH, we forget that in actual fact there is a little covalent bond between those two. Okay? But these are very big and cumbersome. They take up a lot of time and a lot of space to do. So more often than not, it's better to be able to operate in what we call condensed structural formula, which is this abbreviated structural formula, but it still reflects the structure and any functional groups that happen to be in a particular molecule. So it's different from molecular in that if I took the molecular formula of this thing here, I would simply just take all the carbons, okay, of which there are 6. I would just take all the hydrogens, which there are 14 I think off the top of my head, and there's 1 oxygen, so that would give me no indication at all that this was actually 3-methyl pentan 1-all, that molecular formula. Okay, so a condensed structural gives me some information that I could actually go from it and turn it into a full displayed, or if I was a really good student, I could work out from the condensed structural formula of this thing that it was indeed actually 3-methyl pentan 1-all. So if we look at it, and I'll sort of talk you through this, but we'll do some examples anyway. You can see here we have a CH3 group to begin with, and that's that CH3 group there. Then we go to a CH2, okay, that's that CH2 there. Then we have a CH here, okay, and that's it there. We have a little branch then of a methyl group coming on, so I've put it in brackets there to show that it is a branch. Okay, then I have slightly. Okay, then I have again into a CH2 here, so I've written CH2 here, and then I have another CH2 here, and I've written CH2 there, and then at the very end I have an OH. Okay, so you will be expected to be able to operate between those, okay, and to sort of migrate between those various different formulas without really very much effort. Okay. Now, if we're feeling really lazy and we don't want to draw all of this out, we don't even want to do this, okay, and we're really tight for space, we can use what we call the skeletal and sometimes called line formula. So this is very quick, it's much less cumbersome, and it really what it does, it omits any carbons and any hydrogens, okay, or most hydrogens. So if we look at the skeletal formula of this molecule, so you can see the very large, cumbersome, full or displayed structural formula here, and then the very much less cumbersome skeletal formula down here. So how do we come about this? Well, every end or every angle or corner, whatever you want to call it, okay, is represented as representing a carbon atom. So I've sort of put an overlay of red carbons on this one, so you can see where I'm coming from here. Okay, so every time I come to a new carbon, I put a 120-degree bond angle in here. Now, every carbon is assumed to be, if there's a carbon here, which there is, it's assumed to be saturated with hydrogens unless there's something else drawn there, like an oxygen or a chlorine or something else. So in other words, I have a carbon here, there's a bond going there. Every carbon has to have 4 bonds on it, as we know. So therefore, this carbon has to have 1, 2, 3 other bonds, and they're all assumed to be hydrogens. Likewise here, this carbon here has got 1 bond going that way and 1 bond going that way. We know there's a carbon there because there's an angle or corner. Okay, so therefore this carbon can only have 1, 2 hydrogens, so that represents a CH2 group. If we go down here to this side branch, okay, there's an end there, which means it must be a carbon. There's only 1 bond coming off it here. So therefore we must have 1, 2, 3 hydrogens. There's nothing else drawn on it, so that's a CH3 group. It's that CH3 group up there. And then when we get to the end, we have our functional group, okay, and that is an OH, so we just plonk it on the end, really, as I've done here. Okay, and again, you'll be expected to be able to move from name to condensed structural to skeletal, okay, from full structural to skeletal, and all those sort of movements from one to another. So what we'll do is we'll have a go at a few. You might want to perhaps pause the video, have a go at them yourself whenever I give you maybe the name of the molecule that we're going to do, or the displayed structural, and then perhaps you could check that you understand what we're doing. Okay, so that's all the formulas, all about them, and we'll just do a few examples, and hopefully by the end of it you can sort of work your way between. So we'll start off between the various different ones. So we'll start off with something really nice and simple. So we'll do something like 2, 2 dash dimethyl 2,2-dimethyl pentane. So the first thing we might do is, I think probably, is you're going to draw it out, full structural formula to begin with, I think, as an A-level student. Okay, so we will stick everything. I'll not draw my hydrogens in because it just saved me a little bit of time. Okay, so it's 2,2-dimethyl, so this is number 1, number 2. Dimethyl means I've got 2 CH3 groups there, and it's 5 carbons, it's a pent, it's AN, so it's all single bonds. Okay, so that's fine. We can easily now go to our molecular formula, I think is the next simplest step. So we count up the number of carbons, we count up the number of hydrogens. So in this one we have 7 carbons and we have got 16 hydrogens. Okay, so that's the molecular formula. The empirical formula, well, I can't bring this down any simpler. Okay, so those two are the same. Then we're into condensed structural formula. Okay, so here we've got a CH3, so I'm going to go CH3. Then we have a carbon, which has got 2 CH3s attached to it. So I don't write C2H6 for the 2 CH3s. That would be not reflecting the presence of 2 CH3s. So I bracket it. I have CH3 and I have 2 of them. Okay, then we're into our chain. So we have CH2, CH2, and finally we have a CH3, and that's how we might represent a condensed structural formula for that molecule. Skeletal formula, then we have, so we do the backbone first. We've got 5, so we go 1, 2, 3, 4, 5, simple as that. Then we have 2 methyl groups and they're both on position number 2, so we simply do line, line. and that would be our skeletal formula. Okay, so that's a really simple one to sort of get us going. Okay, let's look at something. Like we'll go into something with a slightly different functional group. So we'll do methanamine. Okay, and if we think about methanamine, okay, so meth means one carbon, and amine tells me that I have that functional group. Okay, so let's see what we do then in terms of methanamine. Right, so first of all we would do, again, I think it's simplest to go to our molecular formula, because we just simply add everything up. So we have one carbon, we have 5 hydrogens, and we have a nitrogen. Okay, our empirical formula in this instance would be exactly the same. I've got one of those and one of those, so I can't reduce that any further. Okay, then I have my condensed structural formula. Well, I condense that to a CH3 and an NH2, nice and simple. And then finally I have my skeletal formula. So I have one carbon here, so it's just that, there's my carbon, okay, and that goes to a nitrogen, okay, H, okay, very simple, okay, and that's my skeletal formula. Alright, if we then took maybe something like, let's say, ethanoic acid, something that you should be fairly familiar with, so we'll just, again, simplest thing to do, full structural first of all, I think, and again remember to draw all your bonds out, so don't forget about that little bond there. Okay, then we would do our molecular, so we have 2 carbons, we have hydrogens, 1, 2, 3, and 1 there is 4, and we have 2 oxygens, so that's O2, that's my molecular formula. Then I would have my empirical, and this time it does reduce because everything there is divisible by 2, so it goes to CH2O. Then I would have my condensed structural formula, so I abbreviate that to CH3. Okay, now we have a functional group here, and the way in which we must represent a carboxylic acid functional group is by writing it COOH that. So therefore I now know that that is, because of this, that is a carboxylic acid, and that's a condensed structural formula. I know what the structure is there. Okay, and finally then we have got our skeletal formula. Okay, so in our skeletal form we've got 2 carbons, okay, so we'll have 1 here and we'll have 1 here, okay, now we have a double bonded O to that one, okay, and we have got an OH to that one, okay, so if we were to do that, carbon with 3 hydrogens on it here, carbon with 1, 2, 3, 4 bonds on it, so no more hydrogens on it, and our OH. So that would be our line or skeletal formula to finish off with there. Okay, pretty straightforward, I hope. Okay, right. So we'll do another couple. So let's see here now. If we have maybe a dicarboxylic acid. Okay, and we'll just show you how you would deal with those, and we'll maybe put a couple of methyl groups on it as well. Okay, so we'll put a Br on it, and we'll put a methyl group there. Okay, and we'll put an aldehyde group. So we have an aldehyde group, we have a oic acid, I'll just write for a carboxylic acid, we have a bromine here, so it's a haloalkane group, and we have here an alkyl group, which is of course a methyl group. Okay, so again, the first thing that I think would be the simplest to do would be our molecular formula. So that's just a matter of, we've got carbons in there, we've got hydrogens in there, we've got oxygens in there, and we've got bromines in there, and it's just a matter now of counting them up. So in my chain here I have 3, 4, 5, 6, 7 carbons, and I have 1 down here, and don't forget about that. So I have 8 carbons in total. Hydrogens I have 1, 2, 3, 4, 12, I think, if I've counted them correctly. Double check. Yeah. I have oxygens, I have 2. Okay, and I have just got 1 bromine, so that I think hopefully is us. 13 of those actually. Okay, right, well, because I've 1 bromine, the empirical formula and the molecular formula have to be exactly the same. Okay, so and then we get into our condensed structural formula. So here, this is our carboxylic acid group, and so we represent that as COOH. Probably at A level you'd be fine to write it COOH in that way. I like to write it HOOC at this end, because then this carbon is showing that it's linked to this carbon whenever we go into our CH here with the BR. No need to put the BR in brackets, it's not a side branch. Okay, then we're into CH2 here. Okay, then we're into, CH2 here. Then we're into CH here, which does have a CH3 coming off it here. And then we're into 2 CH2, so just do CH2, CH2. And then we're into an aldehyde group. Okay, and we can't write aldehyde COH, which might be the temptation, because that represents alcohol and will be wrong. So CHO is how we would represent an aldehyde. Okay, and I can now look at that and know as a chemist that that is an aldehyde group. If I wrote that, that would create confusion and would be essentially marked wrong. Right, so that's my condensed structural formula for this particular molecule. Then we have a look at the line formula for it. So again, we will have, let's see, 1, 2, 3, 4, 5, 6, 7. So simply start off with. So just always double check in case you stick an extra one in. So 1, 2, 3, 4, 5, 6, 7. Okay, it's always worth having a double check, right? And then we have our group at the end, which is my carboxylic acid group. That's that sorted. We go through it here. We have a bromine, okay, and we go down to carbon number 1, 2, 3, 4. So double check. Keep 1, 2, 3, 4. We have a methyl group, okay, so that's that done. And then we've nothing else until we get to the end, which is that, and we don't need to put our single hydrogen on. So if we were doing a skeletal formula for this particular molecule, that is how it should look. Okay, so we'll do another couple. I'll take a couple of alkenes. So we'll take, for example, we'll go, I'll just draw it out fully actually, as I have been doing so far. Okay, so we've got what we call and you've probably already met this, it's called a triene, and that's just ene meaning I've double bonds, tri meaning I've got 3 of them. And we've got 3, 7, so we've got a hept triene, okay, on the double bonds are in position 1, 2, 3, and 6, so it's hepta 1, 3, 6 triene. I number from this end because that gives me numbers of 1, 3, and 6, whereas if I went from this end it gives me numbers of 1, 4, and 6, so I always take the lowest numbers, okay. Right, then we would be asked to do our molecular formula. So we have, of course, 7 carbons. Okay, hydrogens we have got 10, I think. So I'm double check. 2. Yeah. Okay. Always good to double check. Empirical formula, well, 7 and 10. So the empirical and molecular is exactly the same again. Condensed structural formula. So we have a CH2, we have a CH, we have a CH2, we have a CH and another CH and another CH and finally a CH2. So if you were given that, you should be able to then go back up and work out that there must be a double bond in here, okay, and there must be double bonds in here as well. And then finally we've got our skeletal formula. So again we've got 7 in our chains, so we do 1, 2, 3, 4, 5, 6, 7. We have a double bond here, and all we do for that is that. We've then got a double bond at the here, and then we've got 1, 2, 3, so we must have another double bond there, and that would be our skeletal formula for that molecule. Okay, so hopefully you're starting to get these guys. I think they're not too bad. I'll do a couple maybe that perhaps aren't on the spec, but you can have a go at them. So we'll have a look at maybe we'll have a look at an ester actually. So we'll do an ester called propyl butanoate. Now it's not on your spec, but I'll draw it out here and then you can work from there. So propyl butanoate, it has a structure as so all the hydrogens in here. Okay, so that's propyl butanoate or propyl butanoate. If we then did our again a molecular formula, so we have carbons in here, we have hydrogens in here, and we have oxygens in here. So our carbons are 7, okay, if we count them up, our oxygens are 2, and our hydrogens are 14. So that's our empirical formula, again, is exactly the same. Okay, I can't reduce that any further. Condensed structural, so if we go condensed structural, so we go CH3, CH2, CH2, C. Now, sometimes you can, this could be abbreviated down to a C3H7. Likewise, this could be abbreviated down to a C3H7, and you'll see that on occasion. I don't really like doing it for this level, to be honest. It can end up getting really very messy and very confusing. Okay, so we're here and we go, we're at that carbon, and then we go OO, and then finally, I'm going to run out of space here, so we'll just go down to here. It's a CH2, CH2, CH3 at the very end there. Okay, so that, if you like, is attached to that. Alright, so you could, I suppose, if you wanted, this could be abbreviated right down to C3H7, COO, C3H7, and that would be fine. That's all one chain, that's one chain. I couldn't take, if there was, for example, that in there, I couldn't lump all of that and make this a C4H10 group. Okay, that would not reflect structural properties of this molecule. Right, skeletal formula, let me just take that back out. So again, we have 1, 2, 3, 4 in this chain. So 1, 2, 3, 4 to there. Okay, and then we're going, now we have this, so I'll just pop that oxygen, which is that oxygen in there. So we got our CH3, our CH2, our CH2, our carbon with the oxygen. Then we have another oxygen here, which is bond in between the two carbons. So that's exactly what we do. We just pop it in there, okay? And then we have at the end, then we have our CH2, and finally our CH3. So that would be the condensed structural formula of a compound with this displayed structural formula. Sorry, that would be the line formula of a compound with that displayed structural formula. Okay, we'll have a look at a nitrile then. Okay, so if you remember, a nitrile has a functional group of C triple bond M. So let's take something. Okay, so again, molecular formula and empirical formula. So we have 1, 2, 3, 4, 5. We have 3, 5, 7, 9, and we have a little nitrogen on its own. Again, because we've one nitrogen, it cannot be reduced any further than it has been there. So empirical and molecular are once again the same. Then we have condensed structural, so we would have CH3, we would have CH2, we would have CH2, another CH2, and then CN. Now again, I could take that right down to, because it's all one long chain, I could take that to C4H9, CN. That wouldn't be a problem in terms of condensed structural. Okay. And then finally we have our skeletal formula. So we've got 1, 2, 3, 4, 1, 2. Okay, so we have a CH3, a CH2, CH2, and then our final CH2, and then we have C, and we put this in as our functional group. Okay, we have C triple bond N in there at the end. Okay, right, and that's sort of how you would deal with that. I think I've kind of covered most bases. I'll maybe do one, I know I've already done one with side chains on it. I think I've covered a fair bit there in terms of those formulas and given you hopefully a good idea of how to deal with them. I've got plenty of worksheets in class if you need any extra help, but hopefully that sort of clears up the difference between empirical, molecular, full structural, condensed structural formula and finally your skeletal or line formulas.